Welcome to AI Paper Podcasts, your shortcut to the cutting edge of machine learning research. Today, we're tearing into a paper that really tries to solve one of the biggest reliability problems out there.
It's a big one.
The paper is called The $4 Delta Bound, Designing Predictable LLM-Verifier Systems for Formal Method Guarantee.
And this paper gives us a much-needed mathematical anchor. I mean, until now, when we've tried to combine large language models with these deterministic formal verification tools, we've just been looking at a giant black box.
Right, with no guarantees.
Exactly. The core problem is there's no guarantee it will ever stop. For safety-critical code, think aerospace, autonomous cars, medical devices, you just can't risk a system that might loop forever or eat up all your resources.
So the breakthrough here is something they call the LLM-Verifier convergence theorem. This is really the first formal framework that gives designers a provable guarantee that their process will actually finish.
And they did it by modeling the whole thing not as some messy generic loop, but as a sequential absorbing Markov chain. It's a really elegant model.
A Markov chain, okay.
Yeah, and it forces the system to pass through 4 mandatory sequential engineering stages. Things like code generation, compilation, invariant synthesis, and finally, SMTSolving.
And the result that an engineer can actually use. A very simple, very precise latency bound. The expected number of tries, let's call it n imolars, to get to a verified state is less than or equal to $4.
And that delta is just the LLM's probability of success at getting through any one of those 4 stages. It's that simple.
And they didn't just stop at the theory. They stress tested this with, what, over 90,000 trials?
They did. And the results were, frankly, startling. They have this metric, the conservative factor, which just measures how close the theory is to reality. And it was always hovering right around 1.0.
Wow.
Yeah. It basically transforms resource planning from this nervous guessing game into a proper, predictable engineering task.
Okay, let's unpack all of that. Let's start with the pain point. For anyone in these critical fields, formal verification, using tools like ESBMC, it's just not optional. You need that mathematical certainty.
Absolutely. FV finds the kind of subtle, bugs-like numerical precision errors or memory safety issues that you could spend forever testing for and still miss.
But LLMs are so good at accelerating the process, they can generate specifications or repair code.
Craft those really complex loop invariants that are a nightmare to write by hand. They offer huge productivity gains.
But the moment you mix them, the statistical probabilistic LLM with the rigid deterministic verification tool, you get this fundamental conflict.
That's the conflict. And without a mathematical framework for it, you run into 3 huge problems that have really stopped these systems from being deployed in critical applications.
The first one is the most obvious: unpredictable termination.
Right. If the LLM is just trying to fix an error, and it can just wander off track, maybe oscillating between a syntax error and a logic error.
And back again.
And back again. You have no mathematical guarantee it will ever stop. And if you're building flight control software, that's just a non-starter. It's unacceptable.
Exactly. Which leads right into the second problem: unbounded resource consumption.
If you don't have a theoretical maximum number of steps, you can't set a reliable timeout.
Yeah.
You can't budget for compute time or memory. The costs just keep accumulating.
And eventually it just crashes the whole application.
It exhausts the resources. It makes the whole system architecture impossible to plan for.
And the third problem is about the LLM itself, this idea of lack of stability. LLM performance can drift over time, right?
It's non-stationary. The context window can fill up. Other factors can influence it. And if you can't connect the LLM's current capability, its skill, really to the total time it's going to take, then you're just guessing about your deadlines and your hardware needs.
The implication is pretty clear. You can't put these systems into production where safety and cost matter unless you get rid of that guesswork.
Exactly. The paper's goal is to replace that black box loop idea with a structured, mathematically accountable pipeline.
So how did they do it? Let's get into the solution, this convergence theorem based on a sequential absorbing Markov chain. For anyone who hasn't thought about Markov chains in a while, how does the model actually work?
The easiest way to think about it is like a set of required milestones, a marathon with checkpoints. The model has 5 states in total.
Yeah.
4 of them are what we call transient states. These are the engineering steps you have to complete. And the 5th state is the absorbing state, which is just verified. Once you get there, you're done. You can't leave.
And the sequential part is really important here, right? You have to do step 1 before step 2. Why is that so crucial? Why can't the system, say, jump from failing at step 3 all the way back to step 1?
That's a fantastic question.
Yeah.
It's crucial because the model is designed to reflect a structured, a sane engineering process. If the SMT solver fails at the end, it gives you a counterexample.
A clue.
A clue that points to a local problem. Usually it's an issue with an invariant or the code right around the error. So the LLM only needs to make a local fix and retry from the nearest prior stage. It prevents the kind of wild oscillation where the LLM just, decides to scrap the entire code base and start over.
I see. So the 4 sequential states are del1, CodeGen, so82 compilation, 3.3 invariant synthesis, and COR SMTSolving, and you have to pass them in that order.
Correct. And the movement between them is governed entirely by the LLM success rate, which the paper defines as delta, the error reduction probability.
So delta is just the chance the LLM succeeds on a single try, moving from stage Siegel to the next one, +1.
Yep. If it succeeds with probability delta, you advance. If it fails with probability $1 delta, you just stay put and retry the same stage.
And that retry logic is where the math gets really clean.
It's beautiful because the time you spend stuck in any one of those states follows a well-known pattern. It's a geometric distribution. And from basic probability theory, we know the expected number of tries to get through that one state is just 1 over delta, $1 delta.
Okay, now the bound makes perfect sense. If you have to get through 4 of those states, and each one is expected to take $1 so all tries.
And the total expected time is just the sum,
right.
$1 dollar plus $1 plus $1 dollar.
Which is $4 dollar.
That's the result the paper really hangs its hat on. Now, there is a small technical detail. The formal expression from the math is actually a bit tighter. It's $4 3 delta delta.
Right, which is always a little bit less than $4. So why do they push $4 deltas as the main bound?
Because for an engineer doing planning, $4 delta is the perfect conservative upper bound. It's easy to calculate, and it guarantees you won't underallocate resources. It just gives you that extra layer of safety.
So we have the bound. What are the key guarantees that this theorem gives us?
It gives us 3, and they perfectly solve those initial problems we talked about. First, almost sure convergence. This is huge. As long as delta is even slightly greater than 0, so the LLM has some chance of getting it right, the system is mathematically guaranteed to eventually reach the verified state.
It won't loop forever.
It won't loop forever. Second, bounded latency, which is the $1 delta bound itself. That gives us the resource ceiling we were missing.
And the third one?
The third is exponential tail bounds. And this is key for real-time systems. It means the probability that you'll need a really, really long run, say more than a total dollar steps, drops off exponentially fast. This gives you the mathematical justification you need to set a hard, reliable timeout. It turns that guesswork into a calculated risk.
Okay, let's ground this a bit more in the tech. The LLM is helping tools like ESBMC. That's a serious industrial strength model checker.
It is, and it relies on a technique called bounded model checking, or BMC.
And BMC is what takes the code and turns it into these logical formulas, the verification conditions, or VCs.
Yes, it unrolls loops. It uses a format called static single assignment, or SSA. It does a lot of complex transformations to create those VCs.
Now, out of all those steps, where does the LLM usually struggle the most? Is it generating the initial code, or is it something trickier?
It's almost always the invariance for the loops, which is stage 3 NFV ProWays. Generating a correct loop invariant requires a kind of deep, logical reasoning about the program state across every single iteration. That's much, much harder for a statistical pattern matcher, which is what an LLM is, than just cleaning up syntax or generating a first draft of code.
And those VCs then get passed to the final stage, $74 SMTSolving.
Precisely. They're fed to a satisfiability modulo theory solver, like Z3. SMT is what can reason about complex things like bit vectors, arrays, and arithmetic. This is the moment of truth. The SMT solver gives a definitive, deterministic answer, either verified or here's a counterexample.
And that really highlights the tension again. The SMT solver is pure logic. The LLM is pure statistical pattern matching, just trying to generate a fix that's logically sound enough to move forward. With that probability, Galto tech.
And we know from other papers that delta dollars can be all over the place, depending on the task.
Yeah.
Something like specification synthesis could have a delta of, 0.88.
Yeah.
But that really tricky invariant generation we just talked about, that might drop all the way down to 0.36.
Which really validates their choice to test across that whole range of delta values in their simulations, from 0.1 all the way to 0.9.
It makes it incredibly relevant. And one last thing on context. For deployment, we almost always have to compress these LLMs using things like quantization or LoRa to make them fast and efficient.
Right.
The key engineering challenge then becomes applying those optimizations without accidentally degrading your delta value so much that you fall out of a stable convergence region defined by this theorem.
Okay, this is where it gets really interesting for me. The empirical validation. They ran over 90,000 Monte Carlo trials. That scale is it's incredible.
It's what was needed to really establish rigor. So their first research question was very simple. Did it actually converge?
And the answer was a resounding yes. 100% success. Every single trial eventually hit verification, which is a huge empirical vote of confidence for the almost sure convergence guarantee.
But the real kicker was the second question. How accurate was the $4 delta bound? Was it a real predictor or just a loose safety net?
To measure this, they tracked the conservative factor, which is just the ratio of the theoretical bound to what they actually saw.
And that factor was unbelievably stable. It just hugged the line at 1.0, barely moving. It ranged from like 0.9942 to 1.0043.
Wait, hold on. So you're saying $4 delta isn't just a worst-case buffer, it's pretty much the exact predicted average time for the whole process to finish.
That's what the data shows. It's a level of consistency I don't think I've ever seen in an AI-powered system. It just completely validates their choice of the Markov chain model.
And it proves that a better LLM means a more stable system.
Directly. The standard deviation, the variance in the runtime, it dropped off a cliff. It went from about 18.8 when delta was low at 0.1 down to just 0.71 when delta was high at 0.9. Higher quality means way less variance.
And they confirm the exponential tail bounds too, which is what lets engineers sleep at night.
Exactly. With a low delta, say 0.1, you'd need to set a timeout of 97 steps to be 99% sure you'd finish. But with a high delta of 0.9, that 99th percentile latency drops to just 7 steps.
So you can actually calculate your resource needs with mathematical certainty based on your LLM's measured capability.
That's the takeaway.
So what does this mean for design? The paper identifies these 3 distinct operational zones based on delta, which seems super practical for project managers.
Right. First, you have the marginal region where delta is below 0.3. Here, the variance is really high. The expected number of steps can be huge, like 40. This is really only okay for non-urgent background tasks where you can tolerate long run times.
Then you get to the sweet spot, the practical region, between 0.3 and 0.6.
This is where you see a sort of phase transition instability. The variance drops a lot, and the average number of steps is in a much more manageable range, say 8 to 13. This is probably the best zone for most general-purpose verification tasks.
And then for the really critical stuff.
For that, you have to be in a high-performance region with delta above 0.6. Here, the variance is almost gone, sigma drops below 1.0, and the average runtime is at its absolute minimum, as low as 4.4 steps. If you're building a real-time system, you have to engineer your LLM and your prompts to operate in this band.
Now, all of this assumes that delta is more or less constant, but we know LLMs can have performance drift. How does the framework handle that threat in a real production system?
It addresses that head-on with something they call dynamic calibration. The idea is you don't just measure delta once and forget it. You continuously monitor the empirical success rate, which they call delta, in real time.
And if that observed delta, hot delta, starts to drop, say it dips out of that practical region you want to be in,
the system can be designed to automatically trigger corrective actions. It could be something simple, like resetting the context window to clear out noise, or maybe adjusting the LLM's generation temperature.
The goal being just to nudge it back into that stable zone.
Exactly, to actively maintain the predictability that the whole $4 delta theorem guarantees.
This is just a fantastic achievement, and it really does seem to replace guesswork with a proper mathematical foundation for building these LLM verifier pipelines. You get predictable latency, you get termination guarantees, all from this simple model.
What's really fascinating, though, is that the current model assumes that delta is the same for all 4 stages, that the LLM is equally good at CodeGen, Compilation, InvariantSynth, and SMTSolving.
Which we've already said probably isn't true.
Right. We talked about how invariant synthesis is likely the weakest link, the hardest part. It probably has a much lower delta in the real world.
That brings up a really important question for what comes next.
It does. Because if you move from a uniform delta to stage-specific probabilities, so you have a delta code, a delta invariant, a delta SMT, and so on, then the formula for the expected time changes. It becomes the sum of $1 for each stage.
So you'd have $1 code plus 1 delta invariant plus dots.
Exactly. And that completely changes your optimization strategy. You wouldn't try to improve the LLM's general ability anymore. Instead, you'd pour all of your resources, all your fine-tuning, your prompt engineering, into fixing the single weakest link in the chain. You'd focus only on the stage with the lowest delta because that one stage is contributing the most to your total expected runtime. Identifying and then surgically targeting that one bottleneck. That's the next frontier for building these systems.